Here's what it looks like when a droplet gets zapped by a laser pulse. You can see that I'm jealous of anyone whose job it is to literally zap water with lasers. You can also see that the laser mostly splatters the droplet rather than vaporizing it. The implication is that completely vaporizing a droplet would probably take even more than the already unreasonable amount of power we were considering. Then there's the problem of targeting and aiming. In theory, this is probably solvable, perhaps even without military-grade equipment. High-speed cameras can triangulate the 3D position of a baseball or football hundreds of times per second to help referees make calls. A similar but more sophisticated system could help track the incoming raindrops. As for targeting, adaptive optics allows for extremely fast and precise control of beams of light. Covering an area of a square meter would require something like 500 direct pulses of light per second. This is slow enough you wouldn't run into any direct problems with relativity, but the device would, at minimum, need to be a lot more complicated than just a laser pointer on a swiveling base. It might seem easier to forget about targeting completely and just fire lasers in random directions. If you aim a laser beam in a random direction, how far will it go before it hits a drop? This is a pretty easy question to answer. It's the same as asking how far you can see in the rain, and the answer is at least several hundred meters. So unless you're trying to protect your whole neighborhood, firing powerful lasers in random directions probably won't help. And honestly, if you are trying to protect your whole neighborhood, firing powerful lasers in random directions definitely won't help.